The energy from the sun is derived from the hydrogen in the sun. The hydrogen is fused to form helium. We should think of the sun as a huge ball of gas. You could fit 1 million Earths inside that ball of gas. The surface temperature of that ball of gas is something like 6,000 degrees Celsius, and at the core it's a staggering 15 million degrees Celsius.
At these extremely high temperatures in the core of the sun, hydrogen nuclei join or fuse together to form helium. And during this fusion, an enormous amount of energy is released. It is this energy that powers the sun.
Eventually that hydrogen will run out, so the sun has a natural lifetime. It will die. It will have an end of life.
But how did the sun begin? Nearly 5,000 million years ago, in a spiral arm of our galaxy, a cloud of gas and dust existed. Young stars were created when part of the cloud started to collapse, forming a protostar. This is how our sun started life. As the gas and dust at the center of the cloud got squeezed together, it started to heat up. The temperature became so extreme that hydrogen started fusing to helium. The sun switched on. The remains of the gas and dust around the sun eventually formed the solar system. Our sun is currently at middle age, and luckily for us, it's stable. But in a few thousand million years, it'll run out of hydrogen in the center. As the energy from the hydrogen fusion reaction stops, the center of the sun will begin to shrink under gravity. Around the helium core, hydrogen continues to fuse. This energy causes the sun to swell up and form a huge red giant. As it swells, the sun will swallow up Mercury and Venus and leave the Earth parched. Eventually, the helium core becomes so hot that the helium starts fusing into, among other things, carbon. The sun now begins to pulsate, until eventually, in one of these pulses, it throws out its layers, forming a planetary nebula. The center of the sun remains, a white hot core called a white dwarf. This slowly cools down, still orbited by the charred remains of the Earth and other planets. But how do we know that our sun will become a red giant and a white dwarf?
If an alien came to the Earth and found one human being and studied that human being, they'd be able to say something about how that person worked, how they breathed, how they could see, something about how their arms and legs worked and so on, but they wouldn't understand anything about the life cycle of human beings. In order to do that, they'd have to see babies, adults, older people, and then they'd know something about the life cycle, how people are born, how they die, and so on. Of course, astronomers are in the same position. We have this star called the Sun, which happens to be close to us. We can study it in great detail, we can understand something about how it works, but to look at the life cycle of the Sun, we really need to look out at the other stars, and we can see stars in different stages of their life in the same way as the people were in that analogy. So you see younger stars being formed in gas clouds, you see stars like the Sun, you see the old red giants. You see stars exploding.
Well, all stars, including our sun, are usually born somewhere like this, and there are stars forming in this cloud of gas and dust. Now, when we study this, we can see that there are stars that are about the same size as our sun, but there are many that are much, much bigger, and much bigger stars have a completely different life cycle. A big star, by being big, signs its own death warrant. Because it's so big, its nuclear reaction goes much, much faster, and it consumes itself in a much shorter time than a star like the sun. And what we can see here with this very large star is that it's already unstable. And so what's happening is you can see that there are these large amounts of gas here, and they are expanding outwards from the center of the star. and the fate for this star is to blow up in a dramatic way, and we call that a supernova. During a supernova, a star will almost outshine an entire galaxy. It gives off an awful lot of energy, and it basically blows itself to bits.
After it is blown up, a supernova ends up as a neutron star, or even a black hole.